In this next lab, we're going to be studying another form of motion measurement. As we know, motion measurement can be accomplished in a lot of different ways using a lot of different types of sensors. We've actually already looked at a couple. In the first lab, we actually used the little gyro on our phones. And in another lab, we used a real simple potentiometer for angular measurement. And when making any of these kinds of motion measurements, you want to make the best selection based on a lot of different requirements based on your application. We're going to be focusing mostly here on vibration, especially so we can introduce the use of accelerometers. In those cases, we want to know, what's the maximum level of acceleration we'll see, and also, if in many cases, a lot of sensors now also have, of course, gyros that can measure angular velocity. We won't be doing that in this lab, but a lot of the sensors that you can get nowadays, and the one that we'll be using in the lab associated with this video is a 6 DOF sensor, which means it has 3 axes of acceleration, 3 axes of angular velocity. So knowing also the range of frequencies, and this is, these are dynamic signals, so we'll introduce the idea of the bandwidth, which is the range of frequencies over which the device is useful to you for measuring certain kinds of frequencies. That needs to be known. And specifications for sensors of these types will have these kinds of specifications on the sheets, the data sheets that you can study and make sure that your device can accomplish what you need it to. If you're trying to measure something like human motion, that's very different from, say, if you're trying to measure suspension dynamics on a vehicle, or the motion of an aerial vehicle, or let's say you're looking at vibration of even an aircraft wing that's very high frequency. So you have to think about that, and you'd like for the device to make the best use of its capability. So 2 words that we'll talk about in another video when we talk a little bit more about accelerometers is sensitivity, which in this case, for example, for an accelerometer is it might be something about whatever you're measuring. Let's say the output is voltage per G, right? So how many volts you get out per acceleration, say measured in G or in meters per second squared, say. And the bandwidth is something that you would measure in hertz, right? So it's the width, and I'll talk more about that again in another video related here. Again, as engineers, we want to be able to understand how these key specifications arise, and so I'm going to talk right now about basic mass spring damper systems, because this is the core of what most accelerometers use. They're sometimes referred to as inertial sensors. They make use of mass spring damper type mechanism to measure acceleration. And many of these inertial sensors, again, are based on these kinds of dynamics. So it's good to understand it. And as you know, in the related lecture for this lab, mass spring dampers form a key part of that lab. So just reminding you, I'll try to also sprinkle in, I talked about this at the introduction of this course, whenever we're studying some kind of physical system and we're attaching a system for making measurements, there's a sensor system that has this mechanism. There's always signal conditioning, and so we'll talk a little bit about that as we go forward. So the mass spring damper, again, something that you study a lot in dynamics, in physics, and 2 very common configurations just to be mindful of. One is, refer to it as a fixed base. The experiment we're going to study is actually a fixed base mass spring damper system, even though it's a beam. And so the base is fixed, and you've got some effective mass, and there's some compliance, some stiffness, and some damping that forms the system. And as you're studying in the related lecture, you're studying constitutive relations, which is the momentum, how it relates to the velocity of the mass, the stiffness, if you had a linear stiffness, how it relates to K, to the stiffness, actual stiffness, and how it relates to the deflection of that spring. And of course, there might be some damping, and if it's linear damping, there might be some damping constant. And in the experiment that we're going to be studying, one of the things that we want to do in practicing how to make measurements and so on is, can we identify some of these parameters, the ones that we can calculate from first principles, and which ones do we have to make measurements of? And so this is the configuration we'll use in our experiment. And another configuration that's very common, again, mass spring dampers can occur in very complex forms. You can have multiple mass spring dampers, but these again are just one mass, one spring, one damper. Another form is where the base is not fixed, but it's actually moving, and you see this a lot in studying vehicle suspensions. For example, this y of t here now is the input, right? The input is not a force at the mass, but rather it's a motion of the base. So you're sort of pushing on the spring damper, if you want to look at that as a suspension, and it's forcing the mass to sort of vibrate up and down, in this case at 1 degree of freedom. And so in this case, we might refer to this as a base excited, because we're exciting the base configuration. And it turns out that accelerometers, inertial sensors of all types, whether they're configured for measuring acceleration, velocity, or displacement, use this configuration. So it's good to understand how it differs. So the model of the fixed base system, which should be familiar to you, we use Newton's law, and we get the basic standard second order linear differential equation, has a force input. You may or may not have an input here, but you certainly have mass, some damping, and some stiffness. Again, this is a linear system, and we often divide by the mass here so that we can define the terms here that are often studied in all second order systems, right? You have zeta, which is the damping ratio, and then the omega sub n, which is the undamped, right, natural frequency. And part of what we're going to be doing in the lab is trying to estimate these parameters, right, from data and also from what we know about the actual system. Just again, some relations that are useful. The undamped natural period is 2 pi, right, divided by omega n. Remember, omega n has units of radians per second. Sometimes if you're going to use hertz, then that's Fn, of course. 2 pi Fn is equal to omega n. This is in radians per second. Fn is going to be in hertz, okay? And those are used, again, depending on what... by the way, the T sub n then is just 1 over Fn, okay? So if you measure the period of something, you can get the frequency, obviously, by just inverting the period, as you know. So let's look at the underdamped second order response, and let's look at that with no input. And we can get what we call an analytical solution. It's a nice linear second order ODE. If it's an underdamped system, that means that zeta, the damping ratio, is between 0 and 1. If you give the mass an initial displacement, say it's x naught, and you also maybe might give it an initial, remember you have to give it 2 initial conditions, you might give it some initial velocity, or let's say you release it from rest. We did this again in other experiments. If you release it from rest, then this might be 0, but not always. Then the solution for that is well known, and we can use that to understand a physical experiment, say. And the response for the system under given these 2 initial conditions, right, given the initial the derivative of the state x and the initial value of the state x, the displacement, say if it's a mechanical system, are used here. Note that you also use the initial condition there. And then this gives you, right, you can plot this and look at the response. Again, this only holds for the underdamped case, which is the case that we'll study in the lab. But remember, when you're studying second order systems, there's a lot of different cases. If zeta is equal to 1, that's a critically damped system. If it's greater than 1, it's overdamped. If it's 0, then it's an undamped system. And it's useful to know those cases. Note that it's only in this case, the underdamped case, where we define also the damped, and it's good to differentiate between the damped and the undamped natural frequency, right? So make note of that definition. It's the underdamped natural frequency, undamped rather, times 1 minus zeta squared. Again, this is for zeta less than 1, right, greater than 0. And that's related to the damped natural period as well. Okay, some relations that will be useful to you in the lab. Just my own rant on notation. I like to say you can dampen your shirt or your emotions, but not motions. Mechanical engineers or engineers and physicists, we use the word damping, right, not dampening, right, for motions. And so try to make it a effort to use damping. I always used to go get frustrated, big Star Trek fan, and I would listen to discussion about inertial dampening on the Enterprise and so on. But the other day, rewatching Alien, I discovered that Captain Dallas of the Nostromo actually uses the right expression as I would use it. He said, all right, inertial damping's going off, right? Not dampening. So my own pet peeve, but you will actually find definitions of dampening and damping. Some people do use dampening in mechanical systems, but strictly speaking, I don't think that's correct. Speak of the undamped case now, is also very useful. Sometimes systems are very lightly damped to no damping, and it's a nice approximation, so it's a good case to think about. And here's the response for the undamped case, really nice little formula. And it's really, where I like to use this is to think about an experiment. In this case, the response is going to be purely in an without any damping. So it's not maybe for the period of observation. If you release it, it's never going to damp. It's going to stay consistently. And so only in this case could you approximate that period right there as the undamped natural period, which would allow you to estimate the omega sub n. In most cases, if you measure this period, it's the damped period. So you need to know two things, right? You need to know zeta and omega n. And so you can't determine parameters without making more estimates. In the undamped case, though, you can. You can right away estimate omega n just from one measurement. And it's a very nice approximation, right? If you're just doing sort of quick back of the envelope calculations, right? So, for example, here's a case, you maybe see you have a mass spring system, you deflect it and you let it go, it's going to oscillate. And it's we used to do real quick experiments this way, very lightly damped system. If you release it at x naught, it's going to oscillate, and you're always going to know that, okay, you know what that displacement is. But let's say you have an accelerometer on here and you're not measuring displacement. You know that if this is going to respond as a cosine, if you release it from rest, then you take a couple of derivatives, and then that means that the amplitude of the measured acceleration, right, that peak right there, and all you have to do is measure that peak, that's equal to the peak displacement of the system times the natural frequency squared. So if you can measure the period, you can estimate, right, you can measure the peak acceleration, let's call that a naught, and from knowing the period, right, without actually measuring displacement, you can estimate it from that peak. Hope that makes some sense. So this is how we use these models in kind of thinking about designing experiments and running experiments and so on. A couple of two more things I want to show you just as a reference. You can come back and look at this. I just gave you some tables here. Whenever you're putting together designs or running experiments, it's really helpful to remember what some stiffnesses are. We're going to be playing with a cantilever beam, and it's this case here. No, it's not this case, sorry. It's this case here. This one shows like a beam where you might have like a torque on it at the end. Here's the beam where there might be a force. And so in this case, say the beam is oscillating. If you had a force here, the stiffness at the end of that beam, you can estimate with this little formula, and that'll be useful to you in this lab. Right, so you just have to know the Young's modulus, the area moment, and then the length L of it, and sometimes again E, the Young's modulus is an estimate, but for most materials we can at least estimate that. A lot of other stiffness formulas here that could be useful to you. And then another nice table here is estimates of undamped natural frequencies. Again, these are estimates, but can work really well. Again, what we do is we throw away the damping, and then we can estimate the undamped natural frequency. And looking at these cases here, here's the one that we're going to be playing with in the lab. It's a cantilever beam with an end mass M. And this forces us to pay attention to the fact that the beam also has some mass, and that's something that you'll be thinking about in the lab. And the actual undamped natural frequency, you can see, accounts for a little bit of that mass from the beam. So this formula also is something that we're going to test in the lab from what we can measure, right? We'll know this, and we'll see if we can confirm that ratio from our measurements.